Welcome to the lecture series of the subject Basic Electronics. This subject is offered to the first year students, and basically this subject gives the overview of the courses which they will be studying in forthcoming semesters. Basically it is an overview of about 8 subjects like circuit and networks, analog communication, digital communication, analog circuit design, from where operational amplifier concept is introduced here. Then there is a brief overview of control system design is also there in the syllabus. In today's lecture, we will be discussing analog communication part. So basically analog communication systems, the student will study entire course in 5th semester. And the name of that course is Electronics Communication System. So in this particular lecture, we will see the basics of analog communication systems. So in analog communication systems, these are the expected learning outcomes. At the end of this lecture, student will be able to draw block diagram of an analog communication system, explain need of modulation, draw waveforms of amplitude modulation and frequency modulation, calculate power and bandwidth for amplitude modulation. And if time permits, we will also discuss the receiving part, that is AM receiver and FM receiver. Now analog communication means we have a analog message. Our analog message can be anything, just like I am speaking now, and microphone is converting my voice into a speech signal. So whatever the electrical output we are getting at the output of microphone is a speech signal, which is being transmitted by Bisect Studio to you. Similarly, there are video cameras kept here. The video cameras are recording my video, so it is also producing a video signal. And these video signals are also being transmitted to you. So analog signals are all real world signals which is generated by microphone, video camera. It can be a transducers, like it's sensing the temperature, pressure, flow. All these transducers will generate information signals. And our intention is to send this information signal to a distant place with help of an analog communication system. So in analog communication, basically the message which is in analog form is being sent to the distant place without converting that message into digital form. So this is the basic analog communication block diagram, where there is a information source. Information source can be microphone, it can be video camera, it can be any transducers, particularly providing an electrical signal which is analog in nature. And then there is a transmitter which transmits the information using a modulation techniques. So in this lecture we will see different modulation techniques like amplitude modulation, frequency modulation and phase modulation. The basic purpose of transmitter is to transmit the analog signal. Just for example, I came today from Rajkot to Bisect Studio with help of my car. So if I consider myself as information, then car will be a carrier for me, because I cannot walk from Rajkot to Bisect Studio, Gandhinagar, because distance is more, 250 kilometers around. So I cannot travel myself without any carrier. So I am using a carrier car. Similarly, person may use a carrier like train, bus, flight. So this will act as a carrier. Once I reach to the Bisect Studio, I park my car at the parking and then I drop that car there. So basic purpose of transmission is that what we will do is that it will help information to reach to the destination. Similarly, my car helped me to reach our Bisect Studio. So now inside the studio, I am not coming with a car because I have parked my car outside. So after reaching at the receiver, carrier is not useful, only information is useful. So at receiver side, we are doing demodulation process. So in analog communication, basically, this receiver part is responsible for a demodulation and transmitter part is responsible for a modulation. And why this modulation is necessary, that we will see in next slide. But between this transmitter and receiver, there is a channel. This channel can be a free space. It can be a coaxial cable. It can be a twin parallel wire. It can be a fiber optic cable. And in any case, in any medium, the noise is the biggest villain in our communication system. Not only biggest villain, but it is also helpful to the communication engineers, because of noise, communication engineer has to work, and they get some work. They get employment because of that. If there is no noise, there are no challenges, then communication engineers will not have to do any job, right? So sometimes noise is helpful to communication engineers, but noise is biggest villain for communication system. Of course, it requires an entire course for the noise, because there are so many different types of noise. There are mathematical derivations that we will study in semester 5th in a different course. So here we will not talk much about the noise, but just you should know that there is some noise present in the channel which will corrupt your signal. So once the signal is received at the receiver, it is demodulated and given to the information destination. Then the carrier signal is very useful to transmit your signal. Basically, your information signal will be modulated onto the carrier. So in this case, the carrier is mathematically representation as instantaneous amplitude small e is equal to capital EC, which is the peak amplitude of carrier, cosine of omega ct plus phi. So where EC is the peak amplitude of carrier, omega c is a carrier frequency, and phi is the phase of the carrier. Now with help of a modulation technique, we modify all these three parameters. So if we modify amplitude of carrier, then it is known as a amplitude modulation. If we change frequency of the carrier, then it is known as a frequency modulation. And if we change phase of the carrier, then it is known as a phase modulation. So these are the three important communication modulation techniques useful for analog communication. Then question may occur in your mind that what is modulation? Then we can say that modulation is the process by which some characteristics of the high frequency carrier signal is changed by instantaneous amplitude of the information signal. An information signal can be anything like a speech, audio or video signal, or it can be any real world signal which we want to communicate to the destination. Then this is one example of amplitude modulation. Let's say that this is a sinusoidal wave which we want to transmit using high frequency carrier. And here we are assuming that high frequency carrier is having a very high frequency compared to the information signal frequency, and that is required actually. Why it is required, that we will see later. But let's say this is the information signal we want to transmit with help of this carrier, then this is the modulation. And you can see here that whenever there is a change in amplitude of information signal, there is always a change of carrier amplitude. You can see here that whenever the amplitude is a peak here, then at the same time you can see that the amplitude of carrier is highest. At this point you can see that the amplitude is minimum, so you can see that the amplitude of carrier wave is minimum. That means our amplitude of carrier signal varies with respect to instantaneous amplitude of information signal. And we are considering here as a information signal as a sine wave, because as a communication engineer we love sine waves, because sine wave is having a very, very beautiful property. See, if you have a sine wave, if you find out the derivative of sine wave, it is also a sine wave. Basically it is a cosine wave, but cosine is also a modified form of a sine wave with a 90-degree phase shift. Only the difference between the sine wave and cosine wave is that 90-degree phase shift. If you integrate the sine wave, then also you will get sine wave. If you add to sine wave, then also you will get the sine wave. And very interestingly, if you find out the Fourier transform of the sine wave, so in a frequency spectrum of sine wave, then you will find that the sine wave is only one frequency present. So it is a very nice waveform, and because of that, normally in all examples, we use the sine wave. You can look at here that this is the amplitude modulation. Then there is a frequency modulation. So in this diagram, amplitude modulation and frequency modulation both are shown simultaneously. You can see this is the amplitude modulation, where amplitude of carriers varies with respect to time and with respect to instantaneous amplitude of information signal, whereas here you can see that the carrier frequency changes. As instantaneous amplitude of message signal changes, here carrier frequency changes. When instantaneous amplitude of information signal is high, the carrier frequency is high. When information amplitude is low, carrier frequency is low. Basically, we are changing the frequency of carrier signal, so that is known as a frequency modulation. And this amplitude modulation and frequency modulation are useful for commercial broadcasting purpose. Then question may occur in your mind that why modulation is required. The first important requirement is we want to reduce the size of antenna. That is the main motive behind the modulation. See, if we transmit our signal directly without modulation, then we require an antenna of the size in kilometers, which is practically not possible because it is related directly with the lambda. As you can see here in this slide, that lambda is equal to c divided by f. So c is basically velocity of light, 3 into 10 raised to 8 meter per second. F is the frequency of the signal which we are transmitting. So now suppose if you consider that my voice, if you transmit without modulation, my voice is having a frequency range of 300 Hz to 3.4 kilohertz. And let us consider one particular component, let's say 1 kilohertz. If you want to transmit 1 kilohertz signal, then if you want to calculate how much size of antenna you require, then you can say that 3 into 10 raised to 8 divided by 1 kilohertz. That means 10 raised to 3. 1 kilohertz means 1000 hertz. That is equal to 10 raised to 3. So if you calculate this comes out to be 3 into 10 raised to 5 meter. If you convert it into kilometer, it comes out to be 300 kilometer. And minimum size of antenna that you require, let's consider a quarter wave antenna case, lambda by 4. Then also you require a 75 kilometer size of antenna. So I will show you this antenna. This is one antenna. So if you consider that if you use a modulation technique, then the size of antenna will reduce. You can see if this is the size of antenna we are using, this is not in kilometer, this is not in meter, this is in centimeter. So if I modulate my voice on 100 megahertz carrier, and using the previous equation, if you find out, and if you say that instead of putting here 10 raised to 3, if I am using 100 megahertz means 100 into 10 raised to 6. So this will comes out to be 10 raised to 8. And if it is a 10 raised to 8 divided by 10 raised to 8, it will cancel out. So the lambda will be 3 meter. And if you are considering a quarter wave antenna, then it is a 75 centimeter. So 75 centimeter is, physically possible. I can extend this antenna size up to 75 centimeter and I can transmit my signal efficiently. And that is only possible if I do the modulation. Without modulation, I require an antenna size in kilometers. Practically not possible to use that antenna. You must have seen the antenna mounted on terrace, that is, a DTH antenna, parabolic antenna. In that case also, the parabolic antenna, this antenna size will increase if you reduce the frequency. And in that case, we are using frequency in gigahertz. That is a microwave range frequency, and because of that, the size of antenna required is less. So as frequency reduces, the size of antenna increases. So the major motivation behind the modulation is to reduce size or height of antenna. Then second important motivation behind the modulation is the multiplexing. Without modulation, we cannot transmit more than one channel or more than one message. Let's say when I was traveling from Rajkot to this bisect Gandhinagar, in between Ahmedabad, I heard the FM station 91.1 megahertz Radio City. Good songs were coming in that. Then 93.5 Radio Mirchi. All are transmitting their own signals simultaneously because they are using modulation. That is called frequency modulation, FM. So that, one message, let's say message X can be modulated on carrier frequency FC1, message Y can be modulated on carrier frequency FC2, message Z can be modulated on carrier frequency FC3. So at the receiver side, if you want to receive message X, you can tune to frequency FC1. If you want to receive message Y, you can tune to frequency FC2. If you want to receive message Z, you can tune to frequency FC3. Like that, you will be able to multiplex all your information signal together, and you can send all the information signals simultaneously on the free space or on any medium. So another possibility is that without modulation, you cannot transmit the signal simultaneously, but if you do the modulation, then it will allow you to do the frequency multiplexing, and because of that, you will be able to transmit so many messages simultaneously. So that is another motivation behind the modulation. Then another thing is that efficient radiation of information signal is possible only at high frequency. At low frequency, the efficient radiation is not possible. So if you try to transmit a low frequency signal on a free space, after certain amount of distance, it will attenuate and it will not reach to the destination. So as you are increasing the frequency of transmission, then the distance automatically will increase. So distance is proportional to the frequency. So as you are increasing more carrier frequency, higher carrier frequency, the distance traveled by the electromagnetic wave will be more. So because there is efficient radiation is possible at high frequency. Effective utilization of electromagnetic spectrum is possible because of modulation. And because of that, we will be able to give a different spectrum to different user. Say for example, if we want to transmit so many audio signals using medium wave, then medium wave frequency is 550 kilohertz to 1600 kilohertz. So here at the separation of 20 kilohertz, we can transmit simultaneously so many audio signals. Similarly, you can see that 2 megahertz to 7 megahertz is a shortwave 1. So it is 5 megahertz band is allocated for a shortwave 1. So if you consider a bandwidth of one channel 20 kilohertz, then you can calculate 5 megahertz, that is 5000 kilohertz divided by 20, comes out to be a 250 audio channels. So 250 audio channels can be transmitted simultaneously in a shortwave 1 band, and similarly shortwave 2 bands 7 megahertz to 19 megahertz and FM radio 88 megahertz to 108 megahertz. Then for a television broadcasting, the different bands are allocated. VHF 1, VHF 3 and ultra high frequency UHF bands are allocated. So these bands are utilized for television broadcasting purpose. Nowadays we are using satellite communication because we have a DTH receiver at home. So we are using frequency in gigahertz to receive the signal from satellite, and it is decoded at our DTH receiver, and video signal and audio signal is separately given to our TV. After it requires so much of processing, and that you will study in audio and video system in 6th semester. So we will not go into much detail in that case. So but the point to say here is that because of modulation, we will be able to utilize the electromagnetic spectrum, and we will be able to plan the electromagnetic spectrum effectively. Important technical terms related to amplitude modulation is a modulation index. Modulation index can be defined as ratio of maximum amplitude of audio signal, or let us say information signal. It can be any information signal like audio or a speech or a video or any other information signal, to the maximum amplitude of carrier signal. And mathematically we can say that modulation index M is equal to EM upon EC, where EM is maximum amplitude of audio signal and EC is maximum amplitude of carrier signal. So EM upon EC defines the modulation index. And these are the amplitude modulation waveforms for a different modulation index. Let's say if I stop speaking, if I am in silent mode, then M is equal to 0 because there is no modulation at all. So our carrier signal remains as it is without any changes. So whenever if you are transmitting a speech and whenever person is silent in between, then M is equal to 0. If my EM is less than EC, that means maximum amplitude of information signal is less than maximum amplitude of carrier signal, then it is a case of M less than 1, which we call it as undermodulation. And if my peak amplitude of information signal is equal to peak amplitude of carrier signal, then M is equal to 1. We call this as a 100% modulation. If my maximum amplitude of information signal is greater than maximum amplitude of carrier signal, then it is a case of overmodulation. But in case of a overmodulation, you can see this envelope represents the information, so your envelope will be clipped here. So negative portion is clipped here. We are considering sine wave here, so you can see that here because of the overmodulation, my negative signal is a negative peak is clipped. That means instead of sine wave, even if I am modulating my speech using M greater than 1, then my speech will get distorted. So I will not be able to recover the speech at receiver side. So we have to take care that we have not to use modulation index greater than 100%. If you use modulation index greater than 100%, then our information signal will be distorted. So we have to take care. So practically in commercial broadcast transmitter, modulation index is kept at 66%. So in that case, M is equal to 0.66. So it will ensure that no distortion will take place. This is a discussion of equation for amplitude modulation. Mathematically, we can say that the carrier signal can be represented with this equation. Instantaneous amplitude of carrier signal EC is equal to peak amplitude of carrier signal capital EC sine of omega ct, where the carrier frequency is omega c, that is radian frequency, otherwise it is called fc. Fc is a carrier frequency. And information signal we represent as sine wave, so it is having a frequency of fm. And peak amplitude of EM. EM sine of omega mt, it represents the information signal. And when we modulate, we get the amplitude modulated waveform. So it can be represented with help of instantaneous amplitude small e is equal to capital EC plus small em, where small em is our audio signal and sine of omega ct is a component of carrier. So our peak amplitude of carrier signal modifies as per the instantaneous amplitude of our audio signal, right? So because of that, we are getting here variation in the amplitude. So you can see that here amplitude varies with respect to instantaneous amplitude of information signal. Further, if we do the mathematical analysis of this equation, you can see here that this equation further you can expand. And it's very simple mathematics that if you consider this as a sine theta 1, sine theta 2, and if you expand this sine theta 1, sine theta 2, it will be nothing but a cosine of theta 1 minus theta 2 minus cosine of theta 1 plus theta 2. Here instead of theta 1 we consider omega ct, instead of theta 2 we consider omega mt. So when we expand this, we get cosine of omega c minus omega mt, cosine of omega c plus omega mt. These are the two components we are getting. Then next, if you take this carrier terms outside, then inside this bracket, you get EM upon EC, and as you know that EM upon EC is nothing but modulation index. So M is equal to EM upon EC. So here our equation simplifies that EC of sine omega ct plus M by 2 cosine of omega ct minus omega mt minus cosine of omega ct plus omega mt. And if you analyze this equation, you will find that there are different terms are available here. The first term available here is a carrier term. EC sine omega ct is a carrier term. this is, you can see that m EC by 2 cosine of omega c plus omega mt is the upper sideband term, and this is cosine of omega ct minus omega mt, this is called lower sideband. So after modulation, you will get three components. One is carrier component, another one is lower sideband, and third one is a upper sideband. Now here you can see this is actually a frequency spectrum of AM signal, and this is a frequency spectrum for actual information signal. See, if you consider only sine wave, then what you will get here is, if you have a sine wave of a frequency FM, then one component you will get here, that is FC minus FM, FC plus FM, and one component will be available here, FC minus FM, and third component will be available as a carrier. But in this case, I am considering information signal which doesn't have a only single component. Then let's say consider that speech signal, it has the entire band of frequency from 300 Hz to 3.4 kHz. So in that case, we have to consider entire band. So this entire band will be around the carrier frequency. So in this case, you can see that in this graph, FC, that is the carrier component. So starting from FC to FC plus FM, all these information components are available here. So this is actually a upper sideband where all this information signal is available. And this is a lower sideband where also the information is available. And here there is a duplication of information. Later on we will discuss the modification in amplitude modulation. That is what we call it as a signal single sideband technique. In that we can reduce a carrier component as well as one of the sideband. So in that case, that type of technique is known as a single sideband technique. If you use single sideband, then also you will be able to recover the information at the receiver side. But for a commercial broadcasting purpose, we are using amplitude modulation. That means along with the carrier as well as LSB as well as USB. And if you find out the bandwidth of the signal here, the bandwidth is nothing but a difference between FC plus FM and FC minus FM. So if you do the subtraction between the FC plus FM minus FC minus FM, you will get 2 FM. That means the bandwidth required to transmit amplitude modulated signal is a 2 FM. So if I have a maximum frequency, let's say 10 kHz, then I require 20 kHz bandwidth to transmit that information signal. If I have a full audio signal of let's say 20 Hz to 20 kHz, then I require a bandwidth of 40 kHz to transmit this signal using amplitude modulation. So in amplitude modulation, we always require a bandwidth of 2 FM. Then let us look at the power requirements of AM signal. The power requirements can be calculated, as all of you have studied in your basic electrical course, that power is nothing but the multiplication between the voltage and current. Or otherwise, you can say it is a V square by R. If you voltage and resistance is given. If current and resistance is given, then it is I square R. So in this case, we have a amplitudes available and we have a peak amplitude available. In a power calculation, we require a root mean square. So RMS value we require. So we have a carrier peak amplitude EC divided by root 2 will give us RMS value. A square of it divided by R. So this is nothing but a V square by R. This is the power of carrier. So if we simplify, it comes out to be EC square upon 2R. So this is the power of carrier. Then similarly, sideband powers. The sideband amplitude as we have calculated in our as per our equation, M EC by 2. That is the peak amplitude of sideband. Then M EC by 2 divided by again root 2 will give us the RMS value of sideband, and square of it divided by R. If you simplify this, it comes out to be M square EC square upon 8R. If you replace the value of EC square by 2R here, then it comes out to be M square by 4 PC. So this will be a sideband power required. Now we are having a one carrier signal and two sidebands. So one carrier signal plus two sidebands. You can see that this is a carrier power. This is the power of lower sideband, this is the power of upper sideband, and if you add together all of these, you will get total modulation power that is equal to PC into 1 plus M square by 2. So this is the final equation for radiated power by amplitude modulation. And you can see that if you increase the modulation index here, then the transmission power will increase because it's proportional to 1 plus m square by 2. So if you are increasing the modulation index, the transmission power will increase. Then let us talk about something detection. Whatever we talked up till now was modulation part, that is at transmitter side. At the receiver side, the antenna will pick up the modulated signal. Then it will be amplified by the amplifier because the signal received at antenna becomes very weak. So we have to amplify that signal. Then we are using RF amplifier to amplify that signal, and then it is converted into IF amplifier, and then it is given to the detector. So in this slide we will be discussing the AM detector part, where our basic purpose is that the input of the detector is amplitude modulated signal shown here. This amplitude modulation signal, we are interested only in envelope. We are not interested in carrier. So we want to extract this information signal, that is which is shown here with a red envelope. We are interested in that. So in that case we can use the diode because now information is available in both the envelope. You can see there is a below also there is a one envelope. So this is the positive side and this is a negative side. If you use diode in this way, it will pass only positive cycles. If you reverse the polarity of the diode, it will pass the negative side. But for an audio signal, it is not much important because human ear is not sensitive to the phase information. So even if you reverse the polarity of diode also, then there is no problem in case of an audio signal. But of course, it is a problem for a video signal. If you are demodulating a video signal, then you cannot change the polarity of diode. Otherwise black will become white and white will become black. So if I have a black hair, then it will appear as a white hair in that case. So in case of a video signal, you have to take care. But in audio, it will not create any problem. Only the thing will happen. Your signal will be phase shifted by 180 degree. Slightly 0.5 millisecond. It will reach later. It will not make much difference for the human ear. So initially this diode will be utilized to pass only one envelope, and then this is a RC circuit basically. So this is considered as a low pass filter circuit where this capacitor can charge and discharge at the rate of audio frequency, but it cannot charge and discharge at the rate of carrier frequency. So carrier frequency is very large compared to the audio frequency. So our time constant of this RC circuit is kept in such a way that it can charge and discharge at the rate of audio frequency, but it cannot charge and discharge at the rate of carrier frequency. So at the output of this circuit, we will only get the audio signal and carrier signal will be suppressed by this circuit, or carrier signal will be bypassed to the ground in this particular circuit. So this is the kind of a low pass circuit we can consider. Another explanation we can give that low pass filter can pass only low frequency. It will not allow high frequency. While our carrier is a high frequency signal, our audio signal is a low frequency signal. So this is a low pass filter circuit which will allow only low frequency. It will not allow high frequency circuit. Because once the signal is received at the receiver, we are only interested in a information. We are not interested in a carrier. So my carrier I have parked at the parking. My carrier was car. When I come here at Bisect Studio, my carrier was car. So whenever I am inside the studio, I don't require a car. So I have parked my car outside. So this detector circuit will park your carrier outside. It will not allow carrier inside the audio amplifier. So this circuit, which is actually output of this audio circuit, will be further given to the audio amplifier, and then it is given to the speaker, so that we will get a audible sound from the speaker. So basically, it will convert your audio signal so that we can listen it. Then let us talk about the frequency modulation. In a frequency modulation, the instantaneous amplitude of carrier signal changes with instantaneous amplitude of audio signal. So here you can see that in this case, here during the negative peak the frequency is less, and during the positive peak the frequency is maximum. So this can be mathematically described as f is equal to fc into 1 plus KEM cosine of omega mt. We can consider here sine or cosine, there is no issue in that, both is same. So basically it will change your carrier frequency according to the amplitude of the information signal. And if you look at the modulation index definition for FM, it is different than the AM. In AM, we have seen that the modulation index is the ratio of peak amplitude of information signal to the peak amplitude of carrier signal. But in case of FM, it is a ratio of peak frequency deviation to maximum modulation frequency. So our signal, which is the information signal, another name given to this information signal is a modulating signal. An output of modulator is a modulated signal. So modulating signal is our information signal, and the highest frequency present in modulating signal is FM. So modulation index in case of FM is defined as delta F divided by FM. Effect of modulation index in case of AM and FM, if we discuss, then in FM, transmission power is independent of modulation index, but bandwidth increases as modulation index. So in a case of FM, even if you increase the modulation index, the transmission power remains same. Only the bandwidth will increase. But in the case of AM, it is the reverse. In case of a AM system, amplitude modulation system, if you increase the modulation index, the transmission power will increase. But there is no effect on bandwidth. Even if you increase or decrease the modulation index, bandwidth remains constant in case of amplitude modulation. Because as we have seen that the bandwidth required in AM system is a 2 FM. 2 FM means FM is the highest frequency of modulating signal or information signal. If you are considering a speech signal, then highest frequency is a 3.4 kilohertz. So the bandwidth required to transmit the speech signal is 6.8 kilohertz. So it will not change even if you change the modulation index. If you are transmitting audio signal of 10 kilohertz, it requires a 20 kilohertz for an AM signal. It will not change if you are changing the modulation index. But if you are using a frequency modulation for a transmission purpose, and if you are increasing the modulation index, then surely the bandwidth will increase. And the bandwidth of FM transmission is usually greater than the bandwidth of AM transmission. And that is defined by, you can find out it with help of a Carson rule. The Carson rule defines the bandwidth for a FM signal. Then let us discuss some modifications of amplitude modulation. If you look at amplitude modulation, it has a carrier as well as two sidebands. And both the sidebands are containing the same information. So basically, it is a duplication of information. So even if you remove one of the sideband, then also, you will be able to extract the information at the receiver. Then such system is known as a single sideband system. And if you calculate the power saving in a single sideband, let's calculate it for m equal to 1. You know that the transmission power of AM system is a PC into 1 plus m square by 2. So in this equation, if you put value of m equal to 1, then you will find that the transmission power is 1.5 PC. Then if you look at sideband power, then sideband power is PSSB is equal to m square by 4. So if you place value of m is equal to 1 here, then you will find that the power required in case of a SSB is 0.25 PC. So which is much less than 1.5 PC. And if you calculate the percentage power saving in this case, then PAM minus PSSB divided by PAM. So if you put the value here of a transmission power of AM 1.5 PC, transmitted power requirement of SSB 0.25 PC divided by 1.5 PC, if you calculate this, it comes out to be 83.33 percentage power saving. So there is a huge power saving if you are using SSB transmission. Then question may occur in mind of the student, then why we are not using SSB at all? Because in a SSB we are getting two advantages simultaneously. One is a power saving and another one is a bandwidth saving. You are transmitting only one sideband. So you require a bandwidth of FM only. You don't require a bandwidth of 2 FM because you are not transmitting two sidebands simultaneously. So we are having two advantages simultaneously. One is the power saving. Another advantage is the bandwidth saving. But still we are not preferring this SSB for a commercial broadcasting purpose because SSB requires a complex receiver. Because here we are removing the carrier, so at the receiver side we have to regenerate the carrier. So your receiver cost increases. So because transmitter is only one, the transmitter power required only one place, but receivers are in lakhs. So we require a receiver simplicity. So commercial AM broadcasting, we are using full amplitude modulation because we want to simplify the receiver. But there are certain various applications of SSB where, let's say police wireless, where we can use the SSB because it is a point-to-point communication. One transmitter, one receiver. So where, receiver complexity is allowed. So, at the expense of receiver complexity, we are getting two advantages. One is a bandwidth saving and another one is a power saving. So there are certain applications like a point-to-point communication, like a police wireless, military applications where we are using the SSB. But for a commercial broadcasting purpose, we are going for a AM transmission, amplitude modulation transmission. So these are the SSB systems. Because it's having advantage, it is utilized for a point-to-point communication, land, air and maritime communication, military communication, police wireless and amateur radio. And it was also utilized in earlier days for mobile communication, which was known as AMPS. It was an analog mobile phone. Nowadays, the mobile is converted into digital communication. So I have removed that points from this slide. But it was in earlier days, it was also utilized for a mobile communication. So these are the different versions of amplitude modulation. It is defined by ITU, International Telecommunication Unit. So International Communication Union has defined A3E as a DSB APC. That is a double sideband with a full carrier. That is your basic amplitude modulation technique. And another one is a R3E. That means it is a single sideband with a reduced carrier. That means carrier amplitude is reduced because the carrier power plays a very important role. So even if you reduce the carrier, there is a useful power saving will be there. Single sideband with a full carrier. Again, the difference between the reduced carrier and full carrier is that if you are using a reduced carrier, then slightly your receiver complexity will be more. But if you are using full carrier, receiver complexity will be less. Single sideband space carrier, where we are totally removing the carrier, we are getting highest power saving, but in that case receiver complexity is highest. Another version is an independent sideband. In independent sideband, in a USB there is one information, in LSB there is another information. So there are two sidebands, LSB, lower sideband and upper sideband. But here in ISB, what we are doing, that information X is there in lower sideband and information Y is there in upper sideband. So we are transmitting simultaneously two information. So using only one carrier, we are transmitting two information channels simultaneously in case of a ISB transmission. Then another version you can see vestigial sideband, where one sideband full and carrier component and partial other sideband is transmitted. This vestigial sideband is utilized for a television broadcasting purpose, where video signal is having a bandwidth of 5 megahertz. If you use full amplitude modulation, then it requires 10 megahertz frequency to transmit the video signal. But because we are using a vestigial sideband, one full sideband of 5 megahertz, then carrier, then some portion of other sideband we are using for a transmission purpose. So our bandwidth is slightly less than 5 megahertz. So in India, we are using 7 megahertz bandwidth for a television signal transmission. But if you are using SSB in that case, you will be able to transmit the signal with 5 megahertz, but your television receiver will become much more complex. So in that case, and even if we are not using amplitude modulation, otherwise the bandwidth requirement will be 10 megahertz instead of 7 megahertz. So to reduce the bandwidth, we are using vestigial sideband technique in case of a television broadcasting purpose. Now let us look at the AM receiver part. In AM receiver, there is a RF amplifier. As I told you, that RF amplifier is responsible to amplify the weak signal coming from the antenna. At the same time, it selects the channel because the different informations are modulated on different carrier. And at the receiver side, we are interested in information which is modulated on carrier frequency, let us say FC1, then we will tune this RF amplifier to the frequency FC1. If you are interested to receive a signal which is modulated on carrier frequency FC2, then we will tune this RF amplifier for the frequency FC2. Then this RF amplifier is given to mixer. The mixer will combine both the frequency, which one is generated from local oscillator and another is generated coming from RF amplifier. It will mix and produce difference of both the frequency. If we call local oscillator frequency as FO, if you call input frequency as Fi, then mixer will produce a intermediate frequency which can be given as FIF, that is equal to difference between the local oscillator frequency and input frequency. So I can say that it is a subtraction between the FO minus Fi. So input frequency is subtracted from the local oscillator frequency and the intermediate frequency is generated. So in case of a AM radio, it is a 455 kilohertz, the intermediate frequency in India. So it is given to the IF amplifier, which will further amplify your signal, but still up till now it is a modulated signal. The detector which we discussed, that was AM detector, is placed here. This is responsible to extract information back from the modulated signal. So output of detector is only a audio signal. So input of detector is a modulated signal and output of detector is audio signal, and that audio signal is given to the audio frequency amplifier and then it is given to the loudspeaker. Then in FM receiver, almost the block diagram is very much similar. RF amplifier, the job is again same as the RF amplifier of AM, only the frequency range is different. Here we are using frequency range 88 MHz to 108 MHz, entire band. Now suppose if you want to listen, Radio City 91.1 MHz, then you will tune this RF amplifier at 91.1 MHz. If you want to listen to Radio Mirchi 93.5 MHz, then you will tune this RF amplifier to 93.5 MHz. So similarly, whatever the stations you want to play, you have to tune at that particular station, and the tuning responsibility is given to the RF amplifier. The mixer will produce intermediate frequency. The intermediate frequency is at 10.7 MHz, and it is given 2 or 3 stages are utilized to get more gain, and will be getting here bandwidth as well as gain both simultaneously if you are using more than one IF stage. Then the signal is given to the FM demodulator. The job of FM demodulator is to extract the information from modulated carrier. So our carrier is modulated by frequency modulation. We will extract the information from that and it is given to the stereo demodulator, and then we will get a stereo output here. The function of AGC is automatic gain control. So if your signal strength will vary at the antenna, then you will be able to change the output. If you can keep the output constant, even if there is a input variations are there, output will remain same because of this automatic gain control block. And I request all the students to have a hobby to create, circuits. I will show you one circuit which is kept here. This is actually FM transmitter circuit. And this transmitter is on 100 megahertz. So this is a microphone which converts your speech signal into audio signal. And there is a circuit here. And this circuit will basically modulate your speech or your audio signal onto 100 megahertz carrier. So in a laboratory, you should develop such transmitter and receiver circuit, and you do some experiments, then only this theory idea will be concreted. So this is one circuit diagram which is shown on the slide. And a lot of circuit diagrams nowadays available, but be careful, you have to do this experiment only in laboratory. Outside the laboratory, it is not allowed. Because if you use this outside laboratory, then licensing problem is there. You have to take license. So, but you can use it for laboratory purpose within your campus, within your laboratory. You can do the experiments. These are some of the references, books that you can refer for more details about this lecture. Thank you very much. If you have any query related to this lecture, you can contact me. My email ID is given in this slide. You can just note down my email ID. It is chvittalani@gecrajkot.ac.in. And help your institute to keep clean. Contribute something. You do some cleanliness activity every day to keep your institution clean. Thank you very much.